Petroleum. Where would we be without it? How many items around you do you think owe their existence to petroleum? Petroleum is not just about fuel for our cars, trucks and aeroplanes. It's about so many other things that we rely on day to day and rarely stop to think about what they're made of. But first, the name. Petroleum is taken from the Greek words for rock and oil. Petroleum, or crude oil, is a naturally occurring, flammable liquid which can range in colour from clear, through green, amber, brown to black, and can range from the consistency of water to that of molasses. Once extracted, crude is refined into a large number of consumer products, from natural gas to petrol and kerosene to asphalt and chemical reagents used to make plastics and pharmaceuticals. Chapter 1. The Early Years. Crude oil has certainly had a colourful history. Some of its early uses were waterproofing wooden boats, and the Romans used it as a weapon, for embalming and lighting. The ancient Persians, 10th century Sumatrans and pre-Columbian Indians all believed that crude oil had medicinal benefits. Marco Polo found it used in the Caspian Sea region to treat camels for mange, and the first oil exported from Venezuela in 1539 was intended as a gout treatment for the Holy Roman Emperor Charles V. Right up until the early 1900s, mineral oil, a byproduct of petroleum, was a regular component found in snake oil, the infamous cure-all wonder treatment. It was one of the less successful uses of petroleum. Until the late 19th century, an oil find was often met with disinterest or dismay. Pioneers who settled the American West dug wells to find water or brine. They were disappointed when they struck oil. Several historical factors changed that. The kerosene lamp, invented in 1854, ultimately created the first large-scale demand for petroleum. Kerosene was first made from coal, but by the late 1880s, most was derived from crude oil. Chapter 2. Birth of an Industry. The modern oil industry was born in 19th century America. Whale oil had been used to light the streets, but this was becoming increasingly expensive as the whale population declined. We already used oil from natural seeps for lighting. It was not long before entrepreneurs began to actively search for oil. In 1859, at Titusville, Pennsylvania, Colonel Edwin Drake drilled the first successful well through rock and produced crude oil. Initially named Drake's Folly by his detractors, Drake was vindicated on the 28th of August when his driller, Billy Smith, looked into the well in preparation for another day's drilling and was surprised to see crude oil rising up the well. Drake's well produced 25 barrels a day, and he sold his black gold for $20 a barrel. When the internal combustion engine was patented in 1861, it changed everything. From 1888, automobiles began to be manufactured in ever-increasing numbers. This increased the demand for gasoline or petrol. The 1900s started with a crucial event in the history of the oil industry. On January the 10th, 1901, a well at Spindletop, a salt dome oil field located at Beaumont, Texas, struck oil at 1,139 feet, sending a geyser of oil over 150 feet into the air. Drilled by Captain Anthony F. Lucas, Spindletop represented a major turning point for both Texas and the entire nation. as no previously discovered oil field in the world had ever been so productive. A number of conflicts in the early 20th century led nations to develop an insatiable need for oil for power and lubrication. Factories, steel-making plants, you name it, everyone needed oil and its derivatives. By the 1940s, oil drilling had developed considerably. Development continued, but at a slower pace. The 1950s saw significant developments, especially in the Gulf of Mexico. Mobile offshore drilling units began to work there in water depths of up to 200 feet. Technological developments continued, especially in respect to drill bits and cements. It soon became common practice for workers to be taken to and back from the rigs by helicopter. Gas and oil began to be produced offshore from the waters of the Gulf of Mexico. Once the 1960s arrived, jet engines, cars, and the roads they drove on created an ever-increasing demand for oil. The refining processes were improved and the petrochemical industry began a new era. The 60s also saw an amazing new material enter the market: plastic. Plastics were a revolutionary new product which everyone wanted. The time for oil had come, and nothing could stop it. Some significant achievements and events happened during the 1960s, including the first multi-platform complex in the US Gulf and offshore diving depths reaching 600 feet in 1967. Technological developments continued at an increased rate, and exploration drilling became much more scientific. Technological advances were being made across the whole exploration and production fields, from bits, drilling fluids, casing, cementing and BOP equipment to MWD tools. All these developments simply fueled the rate of exploration. Developments in technology, different geographical areas, deeper wells and deeper water all lead us to an increase in the risk of a major incident. Most catastrophic oil field exploration and production incidents cause not just loss of life, but damage to the environment, bankruptcy, loss of jobs, and loss of company reputation. In early 1969, Union Oil's Platform A in the Dos Cuadras field blew out. Within a 10-day period, an estimated 80,000 to 100,000 barrels of crude oil spilled into the Santa Barbara Channel, Southern California. At the time of the incident, it was the largest oil spill in U.S. waters, and still ranks third after the Deepwater Horizon and Exxon Valdez spills. In the late 1980s, the world focused on the energy industry as a number of major incidents occurred. These were not all related to the exploration of oil and gas, but significantly there were three in the late 1980s. An explosion and the subsequent fire at the Chernobyl nuclear facility on the 26th of April 1986 led to the world's worst nuclear accident to date. On the 6th of July 1988, an explosion and the resulting fire destroyed the Piper Alpha production platform in the North Sea. As a result of the disaster, 167 men lost their lives. And in the March of 1989, the Exxon Valdez tanker spilled its contents after running aground on the Bligh Reef in Prince William Sound. The accident resulted in between 250,000 to 750,000 barrels of oil being spilled into the Alaskan waters. Located off the north coast of Australia, the Montara blowout started on the 21st of August 2009 and continued leaking for 74 days. It wasn't until the 3rd of November, on the 5th attempt, that the leak was finally plugged, when approximately 3,400 barrels of drilling mud was pumped into a relief well to stop the leak. Thankfully, no lives were lost. The Macondo blowout and its associated oil spill claimed 11 lives and is considered the largest accidental marine oil spill in history. Following an explosion on the Deepwater Horizon oil rig on the 20th of April 2010, a seafloor oil gusher flowed for 87 days before being capped and declared sealed on the 19th of September 2010. The US government estimated that 4.9 million barrels of oil had leaked into the Gulf of Mexico, causing extensive damage to marine and wildlife habitats for hundreds of miles of coastline. Chapter 3. Geology. Rocks and how they are formed. Geology, derived from the Greek words for earth and study, is the science of the solid earth and the processes by which it has been shaped and developed throughout billions of years. Petroleum geologists study various geological elements and tell us whether there is a likelihood of hydrocarbons being present and at what volume. Drilling a test well can cost millions of dollars, so the geologist needs to be sure of the facts before exploratory drilling is conducted. The planet Earth is made up of 4 main layers: the crust, the mantle, the outer core and the inner core. The pressure and temperature alters massively for each layer. The crust is formed out of rock materials and is the thinnest of the 4 layers. The crust makes up approximately 1% of the Earth. The mantle is the thickest layer. Approximately 80% of the Earth lies in the mantle. The temperature of this layer is estimated to be about 1000 degrees Celsius. The outer core measures 2,200 kilometers in thickness and can be regarded as a ball of very hot metals. As the Earth rotates, the outer core, consisting of iron, spins over the inner core and generates the Earth's magnetic field. This factor is responsible for the functioning of magnetic compasses. The inner core has an extremely high temperature and pressure condition. The temperature of the inner core layer is greater than the temperature of the Sun's surface. The thickness of this layer is believed to be approximately 1,250 kilometers. In order to better understand how the Earth has been shaped over the ages, we must also consider the Earth's crust. The Earth's crust is made up of a series of rigid plates. The plates form the Earth's surface and float on the mantle, and are known as tectonic plates. Movement between these plates, both towards or away from each other, has caused and continues to cause the major geological features of the Earth's surface, such as mountains, valleys, and oceans. Tectonic plate movement is most likely caused by convection currents from the molten rock below. The molten rocks are like water boiling in a pan, constantly moving and bubbling, with the hottest liquids rising to the top and the coolest moving to the bottom. Friction between the tectonic plates stops them constantly moving. However, over time, pressure builds up, and when the pressure becomes too much, the plates move, resulting in a volcano or an earthquake. The Earth is around 6.5 million meters in diameter, or 21 million feet. The deepest wells currently drilled are in excess of 38,000 feet, straight down towards the center of the Earth. It would take approximately 276 of these deep wells, drilled consecutively, to reach the center of the Earth.
In order to better understand rocks, we need to look at the rock cycle. The rock cycle is a series of constant processes through which Earth's materials change form over time. This animation will take you through the rock cycle. As you move through this animation, click on each of the boxes to learn more about the processes in different types of rock. Understanding uplift is in many ways the key to understanding the rock cycle itself. Uplift is the process that lifts up rocks buried deep beneath the surface to form hills and mountains on the Earth's surface. Without uplift, the Earth's surface would be flat. Mount Everest is made of limestone that must have originally formed on an ancient seafloor. We know this because it contains fossils of marine creatures. Scientists believe that if all the rock cycle processes ceased, then our planet would no longer be able to support life.
Chapter 4. Hydrocarbons and where they are found. The deposition of sediment is very important when considering how hydrocarbons form. When organic debris, such as decaying plant life, sea creatures, animals or plankton, is deposited into rivers, streams or oceans, it becomes trapped in layers of sediment which compact over time and form sedimentary rocks. As the type of sediment deposited changes, layers and layers of different types of sedimentary rock form. As the compacted organic material is now far away from any oxygen, and moving closer to hot magma, it gets more and more compressed and heated over time. This heat and pressure then cooks and transforms the organic material into what we now know as hydrocarbons. Under pressure from the huge weight of rocks above, along with the intense heat from its close proximity to magma, the transformation process starts. Over 3 million to 300 million years, if conditions are right, the carbon material in the rocks transforms into hydrocarbons. If the temperature is too high, the material will carbonize, and there will be nothing left at the end of the cooking period. Hot, but not too hot, and gas will form. Whereas, if the conditions are slightly cooler, oil will form. The cooler the cooking temperature of the materials, the thicker the oil. So how do hydrocarbons accumulate in such large amounts? Well, the answer is migration. Oil is lighter than water, so as we know it will float to the surface. Gas is lighter than oil, so the natural tendency is for hydrocarbons to migrate towards the surface of the Earth. They will continue to do this until they're stopped, and as we've seen, this requires an impermeable structural trap. These traps are formed by Earth movements and maybe domes or anticlines and faults, amongst others. Some hydrocarbons find their way to the surface, seeping out of the Earth, but most hydrocarbons become trapped in accumulation sites. So, why do hydrocarbons become trapped? This is due to layers of impermeable rocks, such as shales. These impermeable rocks act as cap rocks, preventing the hydrocarbons from further migration. As the hydrocarbons build up, they form an accumulation. The areas the hydrocarbons accumulate in are known as reservoirs. Within reservoirs, we usually find gas at the top, oil underneath, and water at the very bottom. So what is meant by porous and permeable rocks? Porosity and permeability are two of the main features that control the movement and storage of fluids in rocks and sediments. The porosity of a rock is determined by the spaces or pores between the individual grains that make up the rock. The more tightly packed these grains are, the lower the porosity of the rock. The permeability of a rock measures the ease with which fluids can flow through the rock. Most reservoir rocks are both porous and permeable, as they allow hydrocarbons to collect inside them, porosity, and to pass through them, permeability. We will now take a closer look at each of these features. A piece of sandstone, or limestone, is very much like a hard sponge. If you took a domestic sponge and soaked it in water, the porosity of the sponge is the volume of water the sponge is able to soak up. Rocks bearing hydrocarbons hold the hydrocarbon fluids within the rock in the same way the sponge holds the water. The rock's porosity traps the oil inside. In sedimentary rocks, the porosity depends on grain size, the shapes of the grains, and the degree of sorting and cementation. Let's now take a closer look at permeability. It is possible for a rock to be extremely porous and yet nearly impermeable. This occurs when the pores in between the grains are not interconnected. The fluid then becomes trapped within individual pores and cannot pass through or connect to adjacent pores. Pumice or shale are examples of this type of rock. They have a high porosity, yet due to poorly interconnecting pores, some can be almost impermeable. In contrast, some sandstones can be both highly porous and highly permeable. This is due to the well-rounded sand grains, which provide unrestricted pore space between grains. The pores are free from smaller grains and are very well linked. Consequently, sandstones of this type have both high porosity and high permeability. Let's have a look at some rock types to show you an example. Igneous rocks are usually crystalline. This type of rock has almost zero porosity and permeability because there are no real gaps between the crystals. Shale is a good example of rock with high porosity and low permeability. High porosity due to the pore spaces between the individual layers of clay minerals, but low permeability because few, if any, of the pore spaces are interconnected. This also makes shale an excellent seal or cap rock for reservoirs. Sandstone, as previously mentioned, can have both high porosity and high permeability. This is the case if the individual grains are well rounded, with plenty of space between them, and the pores are well connected. Limestone will also typically have high porosity and high permeability. However, unlike sandstone, it is also very soluble, meaning it can dissolve in water much more easily than other types of rock. This is yet another way limestone achieves high permeability and porosity. Water can expand the cracks and fractures already within the rock. Place your cursor over the images to see each rock in microscopic detail. Chapter 5. Geology and the Petroleum Industry. Geologists will look at 4 general geological features when looking for hydrocarbons: source rocks, trapping structures, reservoir rocks, and seal rocks, or, as they are more commonly known in the petroleum industry, cap rocks. Source rocks are the sedimentary rocks, typically shale or limestone, which contain the organic carbon material that will generate petroleum under the right conditions. The hydrocarbons, once formed in the source rock, will usually migrate upwards through other porous and permeable rocks. The hydrocarbons stop this migration once they reach a cap rock. This is known as a structural trap, under which the hydrocarbons accumulate. Geologists search for these structural traps. Within the structural traps, porous and permeable rocks, usually sandstone or limestone, form the reservoir. The geologists will look for the sedimentary source rocks where hydrocarbons could have formed. They will look for possible reservoirs or traps in the rock layers above where hydrocarbons could have accumulated, and then they will analyze, as best they can, the various rock layers to determine their likely porosity and permeability. This will help them to determine the likelihood of hydrocarbons being stored within the rock layers, as well as how easy or difficult the hydrocarbons will be to extract. Chapter 6. Exploration for Hydrocarbons. We now know the type of rocks we are looking for, so we need to find a structural trap. There are a number of ways that we can map the subsurface structure of the Earth. The most important is the Seismic Survey. In the very early days, when oil could be found near, or sometimes even above the surface, it was quite simple to drill a shallow well which would pierce the reservoir and allow the hydrocarbons to flow to the surface. Nowadays, we need to look deeper for hydrocarbon accumulations, and in order to save time and money on endless exploratory drilling, we use scientific methods and techniques to look deep into the Earth's layers of rock. Looking at the surface of the Earth, geologists can tell quite a lot about the rocks that lie beneath. Using aerial photographs and satellite images, even more information can be gathered. But the most accurate and detailed geological survey which can lead to the extraction of oil is a seismic survey. Seismic surveys are used to map the underground structure of rock formations. Geologists interpret the seismic data in order to locate structural traps that could potentially contain hydrocarbons. So, how does it work? The general principle is to send sound waves into the Earth. As the sound waves reach each type of rock formation, the flow of the wave is impeded. The wave literally bounces off the rock. The reflected wave is then recorded using ultra-sensitive devices called geophones and hydrophones. The recorded waves are then converted into electrical impulses, which are then used to build up an image of the underground rock formations. Petroleum geologists then interpret this data to determine rock structures and ultimately to locate oil and gas reservoirs. As computers have developed over the years, the ability to interpret seismic data has increased. The complexity of the seismic tools have also increased, allowing us to send more complex patterns into the rocks and collect more and better data. The overall result is that the images we are able to create from the data are getting better and more accurate. Once the development company has the results from the seismic survey detailing the structure beneath the surface, the only way we can absolutely prove the presence of hydrocarbons is to drill. Well done, you've reached the end of this module. You should now be able to recall some of the early uses of crude oil, outline the origins and growth of the oil industry, recognize significant well control events and technological developments, describe why geology is important to the petroleum industry, explain how hydrocarbons are formed, describe where hydrocarbons are found, and identify different methods for finding oil and gas. Thank you for completing this training module.